Yeah, so before we go for today's lecture, just a recall of what we discussed in the last class, if you remember. Okay, so it's been, I think, more than a week since we had a lecture. Okay, so do you remember what we exactly discussed? Okay, so we discussed about pipeline data path and control. Okay, so how exactly did we make the single cycle data path into pipeline? So how did we make the single cycle data path into pipeline? Using resistors. Okay, so at the end of each stage, you have something called as resistor, which you call it as pipeline resistors. If it is used in pipeline processor. Okay, and then there was one more important modification that we did to the data path. The earlier data path was not correct for pipeline implementation. We made one modification. Do you remember what was that? What was the modification that we did with respect to the data path? There was some very major error which we corrected. So it's basically about the right range value. Okay, so right range value is supposed to be supplied by the instruction, which is there in the write back stage. So you have to make sure that the right resistor number moves along with the instruction. Okay, and then you reroute the right resistor number through the pipeline resistors, and then you connect it to the right resistor pin or right resistor port of your resistor file. Okay, so that was one modification. And what about control signals? How are control signals generated and how are they used? The control signal generation is same only. Okay, the way that you had generated for single cycle, the same way you generate the control signals, but the usage here is different. So how do we use the control signals? Do we generate control signals and use them in a single stage only, or what do we do with respect to the control signals? It's very similar to the right resistor number. Okay, control signals are not used at the same time. They also are sent through the stages. And in each stage, the signals corresponding to that stage get used up. Okay. So can you tell me the control signals which get used up in ALU stage? What are the control signals which get used up in the ALU stage? There are two, if I want to give a hint. So ALU op is one, ALU source is one. So both are used up there. Again, if you talk about memory in memory, they'll be used up in memory stage. And then what will be used up in write back stage? What signals will be used up in write back stage? There are again, I think, two signals. One is mem to reg. The second one is write to write. Okay, so both of them will get used up in the write back stage. Okay, so this is how the control signals also flow. And at the end, we discussed about how exactly the hazard occurs with respect to the space representation. I think that showed you how exactly the instructions move. So we'll just continue with the same discussion. Okay, and we'll try to see how to detect the hazard and how do you come up with a circuit for it. So all of those things will start going through from today's class. Okay. So as we had discussed last time, so we'll assume some initial values of S0, S1, and S2. Okay, so we have assumed S0 to be equal to 0, S1 to be equal to 1, S2 to be equal to 2. So at the end of this, you want S0 to be equal to 3, and that 3 should be used up here and used up here. Okay. But if you have seen if you don't take care of forwarding, if you don't implement forwarding, so if you execute pipeline these instructions in a normal pipeline fashion, then S0 value which will be used will be equal to the old value. Okay, so old value which is 0 will be used. Okay, and then you might get wrong results. So those things we have seen. We'll just again touch upon that and then we'll continue our discussion. Okay, so as at the end of clock cycle 1, you know that the information related to first instruction will be loaded up here in IF/ID register. And again, these are the pipeline registers that you have: ID/IF/ID, ID/EX, EX/mem, and then mem/write back. And at the end of second clock cycle, S1 and S2 would have been read, which is 1 and 2. And your S0 is basically your destination register. Now, till here, there was no problem, but here the problem starts. Okay, so at the end of clock cycle 3, what happens? The S1 plus S2 is computed, which is 3, and which is supposed to be written into S0. But the problem here is at the end of clock cycle 3, your second instruction, which is add S3, S0, S1, has already read a value which is not correct. So S0 is being taken as 0. But in fact, S0 has to be taken as 3. So from here, the problem starts, what you say, accumulating, or the problem starts occurring in the execution. So at this point, we use a concept called as forwarding. Okay. Now there are two types of forwarding. So one of the types of forwarding is called as X to X forwarding. Okay, or we generally call it as X forwarding case. Okay. So here what happens is we try to forward a value, okay, which is already available at the output of ALU stage to the input of ALU stage. So in the next clock cycle, what happens is instead of reading 0, which is incorrect, you read the correct value, which is 3. Okay, correct value, which is 3 for your destination register S0. Okay, and then you will be calculating the correct value for S3. Okay, so if you forward this way, 3 will be taken instead of 0. Okay, instead of passing 0 for the ALU, 3 will be passed. Again, you need a multiplexer here, which will pass either 3 or 0, depending upon some conditions. We'll see what those conditions are a little later. For now, 3 will be passed to the input of ALU, and at the end of next clock cycle, so you will see that. But again, at this point, you have to detect, right, when exactly you have to forward. Okay, so this 3, I said that it should be forwarded to the input of ALU. So what is the condition? When should I forward for X hazard? So we are talking about X hazard, remember. Okay, I'll tell you about the difference between X and mem hazard as we go on. Okay, so this is a case of X hazard where the value of S0 is already calculated. Okay, but you're reading still old value of S0. So we forward from the output of ALU to the input of ALU. So that is basically the case of forwarding. How do I know when to forward? So what is the condition for forwarding? So we have already discussed this also. What is the condition for forwarding? Just in normal English terms, don't worry about RSRT. Just if you are talking about just these two instructions, what is the condition under which I should forward? Okay, the condition is the destination of your first instruction. If it is same as source of your second instruction, then you have to forward. Okay, so that condition is matching here. So this is your first instruction, this is your second instruction. If the destination here matches with the source here, I should be able to forward. So I should be able to detect that condition. So for detecting that condition, which register should I access? Which pipeline register should I access? So you know that the destination register, which is there in the RD field, is available here in the X/mem register. But you want to check that with, if you take the normal data path, you don't actually send RS1 and RS2 to the pipeline stage. You only send the destination register. So at this point, I will not be able to detect. Although I have the register RD value, which is coming from X/mem, okay, I don't have the RS1 or RS2 value, which is supposed to be there in ID/EX register, because then only I'll be able to know what exactly is this source, right? So here that information is not passed in the original data path, so you have to modify. So what modification I have to do? I have to basically connect this RS1 and RS2 also to the ID/EX register, and I have to make sure that I pass those values to ID/EX register, meaning one extra stage you have to propagate the RS1 and RS2 values. Okay, only one stage is enough, as you will be seeing. Okay, you have to pass this only for one stage, because forwarding will be done at this point. You need the contents of source, the information about the source registers, only in the ID/EX stage. Then you will be able to compare. Okay, so here one of the conditions is matching. So your destination, which is there in the RD field, is matching with the source. Okay, so now there are two possibilities. So it could be in the RS1 field, or it could be in the RS2 field. You have to check for both the conditions. So here, what condition is matching? Is it there in the RS1 field or RS2 field? What condition is matching here in this example? Is the destination of first instruction there as the first source of the second instruction, or the second source? It's basically the first source. This is your RS1 field, right? It is there in the first source. So this condition is getting satisfied. At that time, you have to forward. and then you will be able to calculate the correct value. So S3 now is supposed to be written 4 because S0 was taken as 3, which is the forwarded value, plus 1 is there in S1. So 4 is supposed to be loaded into S3 register. Okay, so till this point, again, it is fine. Now coming to the condition. So here there is one more forwarding is required. So that is a case when the destination of the first instruction is same as the source of third instruction. If this is my reference, this is first, second, and third. Okay, so if there is a dependency between first and second, then we call it as X hazard. Okay, the reason is we forward from the output of EX stage. So that is why we call it as X hazard. But there is another possibility of hazard, that is when you have the destination of first instruction to be same as source of third instruction. So till this point, okay, your value of S0 is not updated. But again, in the third instruction, also you want the value of S0. So here also wrong value will be read, whereas the correct value will be here. Okay. So in this case, from which stage will I forward? From the output of which stage will I forward, and where will I forward it to? So in the earlier case, we forwarded from output of EX stage, okay, to input of EX stage. So that was your X hazard. So here, how should I forward? So here, wrong value of S0 is being read, whereas the correct value is here. So in this case, you have to forward the value from where? Where should you forward the value from? So from output of mem stage. Okay, so specifically mem/writeback register, here specifically EX/mem register. So from the output of mem stage to where will I forward to? That is always the same. So to the input of EX stage. So this we call it as mem hazard. Okay, this we call it as mem hazard. So the actual forwarding will be like this. Okay, so you have to forward 3 to the input of ALU, which is there in mem/writeback register. Now, can you tell me how do I detect this condition? The condition where there is a dependency between first and third instruction. How do I detect the condition? Can you come up with a one-line equation for it? Just like we did for the other case. Can you come up with a one-line equation for this condition? Which pipeline register should I check? What value should I check? So which condition should get satisfied for this forwarding to happen? Okay, this forwarding should not happen always, right? So you have to come up with the condition. So what is the condition? Again, it should not just say RD is equal to RS1 or RD is equal to RS2. It is, again, that is true for earlier case also. Now you have to talk about pipeline registers also. Now the destination register that is available in the mem/writeback, if that is equal to the sources that are available, one of the sources that are available in ID/EX. Okay, so if mem/EX register destination is equal to one of the sources RS1 or RS2 of this instruction, that is the third instruction, then again we have to forward. But this case, under this condition, we have to forward from output of mem/writeback register. But in the earlier case, we forwarded the value from EX output of EX/mem pipeline register. Okay, so some data is stored here that you had it forwarded earlier. Now some value is stored here that you have to forward to the input of ALU stage. Okay, so this is basically how we come up with the conditions. But these conditions are not complete. Okay, so there are some cases where these conditions might create problem. Okay. So I'll talk about those cases. Again, once the forwarding is done, you know that the correct value will start propagating. And at the end of clock cycle 5, your S0 value will actually get updated. Okay, till previous cycle, till fourth cycle, your S0 value is still 0. But at the end of fifth clock cycle, 3 would have been written into the register file, and you would still get correct values. Even though it is being written now, you still have already calculated the correct values for S3 and S4. So that is how forwarding will help you to resolve the hazard. Okay, but there are some issues with the forwarding. So these conditions are not enough. We'll talk about why that is the case. So first thing is some instructions do not write into the registers. Okay, So this condition, the forwarding condition, when will it apply? Only if you are writing something into the register. Okay. So if you are writing something into the register, and if that destination is same as source in other case, only then we talk about forwarding. Okay. In other cases, we should not forward. Now, how do I know whether a particular register is being written in this first instruction? First instruction, whether some register is getting modified or not, how will I note that? What signal will tell me whether whether a register is getting modified or not? Any idea? There is only one signal which will tell you whether a particular register is being written or not. Okay, that is basically regwrite. If regwrite is one, only then something will be written into a register. Okay, so that is one thing. Okay, so some instructions do not write into the register, hence the above conditions might lead to forwarding when not required. Okay, so in that case, you might forward wrongly. Okay, so this will happen when some junk data. So, for example, in BEQ instruction, in store instruction, the RD field is not available. Okay, in both of these cases, the RD field is not available, but some data will be there in the RD field, right? Okay, so if you take the store instruction or BEQ instruction, there is no RD field, but some binary value will be there in the corresponding RD field. Okay, so that should not lead to a problem. Okay, so that should not lead to a problem. So that is why we check if a particular instruction is actually writing. Only then we all of this forwarding will come. Okay, so that is first condition. Now there is some cases where some resistors are used as constants. Okay, can you give me an example where some resistors are used as constants and they should not be modified? So for example, if you take this, yeah, exactly. So if you take this, these two instructions. Now tell me if there is a hazard or not. First thing, is there any data hazard? Is there any data hazard? No. Okay, there is no data hazard because whatever you try to write something, if you ever again, whatever you try to write into zero, the value of zero register will not change. Okay, when you see this, zero will only be read from this register. But according to our condition, what happens? Okay, so for example, if you might get forwarding this because the destination is matching with the source. Okay, so in this case, a forwarding might happen. But is this forwarding correct? It is not correct because zero register content will not be modified ever. Okay, so I'll show you that example how to tackle that. Again, the solution to check if a particular instruction is being will write into a register or not is to check for regwrite signal, as many of you already pointed out. And in this case, you have to make sure that. So how do I avoid this forwarding? If I take the current conditions that I have implemented, if I execute these two instructions, it will forward the value. Let's say S1 is equal to 3 and S2 is equal to 4. So what will happen is, although destination is 0, at ALU stage, these two will still be subtracted. Okay, let me take these as 4 and 1. So S1 will be subtracted, like S2 will be subtracted from S1, and then one value will be there. Okay, it will propagate through the pipeline register, but whenever it is supposed to write, it will not write because the destination is 0. Okay, until that point, the value will still go along with the destination register through the pipeline stages. So in that case, it will create a problem. Okay, so we have to avoid forwarding a non-zero value. So how do we do that? We'll see the problem. Okay, so solution is basically to check whether the destination is 0 or not. But let me show this problem in the pipeline representation. Okay, so let us assume that these are the instructions that are to be executed. Now, what happens? Initial values of S1 and S2, let's assume to be 1 and 2. At the end of clock cycle 1, you know that the data related to first instruction loads in IF/ID register. In the second clock cycle, you have 1 and 2, and all the destination register source 1, source 2 are available here. Now, if I move one clock cycle later, okay, so at the end of clock cycle 3, now this problem starts happening. Okay, so here what happens is S1 would have read, which is 1, S2 would have read, which is 2, and then you would have calculated the sum because You are just saying add instruction. So till that point, ALU will not have any information about whether the destination is constant or some other register. All of that information it will not have. It will only have the information that the instruction is add. So it will compute the value in as 3. And then the destination register is supposed to be 0. Now here, if you check the source of the this instruction and destination of this instruction, they are both same. Okay, so your original condition is getting satisfied. So it will forward 3. Okay, and when you compute the sum next time, it will take 3 plus 1 and try to calculate 4 as the result of S3. Is that correct? Is this correct? No. So how do I avoid that? What modification should I do to my original conditions then? So can you repeat original conditions? Again, don't by heart those conditions. Try to understand. Okay, try to understand how exactly the signals are going. So I am taking time to explain all of this so that you don't by heart those equations. You should be able to analyze and you should be able to come up with the equations on your own. Okay, so tomorrow I might give you some different data path where the conditions might be totally different. Okay, so in this case, can you tell me the original conditions? Okay, for X hazard, what were the original conditions? What were the original conditions? Original condition was I have to check EX/mem, the RD field in EX/mem, if it is equal to ID/EX RS1 or RS2 field, okay, or ID/EX, okay, RS2 field, then I have to forward. Okay, so this was my original condition. So how do I modify this original condition so that it takes care of both the problems? One problem is some instructions do not write into the register, so I should include that also. And there is one more case where we talk about constants. So can you modify this equation and tell me the correct equation for X hazard, including both these cases? So yeah, so both these cases I have to include, I have to modify and come up with new equations. And okay, EX/mem RD. Okay, so we should check that if this is 0 register or not. So since in RISC-V and MIPS you have only one constant register, that is 0. Okay, so what you do, you just check. So apart from checking this condition, you also have to check one case, which is your EX/mem RD field should not be equal to 0. Okay, this is your second condition, additional condition that you check. Okay, so this is condition which will tell you when to forward. Okay, so now you have checked this. Additionally, I have to check whether something is getting written right by the first instruction. How do I check that? How do I check that? So this is again, this is like part of it. So can you tell me the exact condition? Regenerate is equal to 1 is fine, but where is that regenerate signal? That also, it's not that it is generated at the control unit, right? Here also regenerate will be there. Here also regenerate will be there. Here also regenerate will be there. Here also regenerate will be there, corresponding to different instructions. Which regenerate should I consider? The regenerate corresponding to the instruction that is available in EX/mem. So hence I should say and, okay, and EX/mem dot regenerate, okay, should be equal to 1. Okay, only under this case I should be forwarding. Okay, so for X hazard, the first condition is your destination in EX/mem register should match one of the two sources that are available in ID/EX register, and the destination register should not be equal to 0, and the instruction should be writing into the register. So that we check by checking X/mem dot regenerate is equal to 1. Okay, hence the actual condition will now be all of these. Okay, and regenerate should not be equal to 0. Okay, and your register RD should not be equal to 0, and your regenerate signal should be equal to 1. So this is like complete condition for detecting X hazard. So X hazard detection, there are two cases. So one is like your regenerate should be 1, your RD should be 0. and your RD matches with RS1. This is one possibility. The other possibility is your RD matches with RS2. So here RS1 slash RS2 I have represented with two different equations. Okay, so these are the conditions for X hazard detection. Now, what about MEM hazard detection? Can you modify similarly MEM hazard detection and tell me the equations? At least for this case, okay. So let's say RS1 is where the matching happens. So can you tell me the equation for MEM hazard detection and forwarding? When should I forward in the case of MEM hazard? Yes. So only few things will change here. Okay, what will change? What will change? So on all of these equations, because the instruction would have gone to the next stage. In all of these equations, you just replace ex slash mem with, okay, just replace ex slash mem with mem slash write back. Okay, so this write is equal to 1, equal to 0, and id slash ex2, id slash ex dot register rs1 rs2, that will remain the same. Only thing that you have to replace is from ex slash mem, you have to replace it to mem slash write back. Okay, so that is your mem. Let me call this as A. Okay, the X hazard conditions, I'll call it as A. This is important. We'll come to the importance of this a little later. Now, normally we can detect mem hazard by changing that. So you have mem slash write back is right. Mem slash write back register RD should not be equal to 0. Mem slash write back register RD should be equal to id slash ex register 1, because the dependency is now between first and third instruction. And the first instruction is in the mem slash write back pipeline stage. The third instruction will be there in the id slash ex stage. So hence you check for id slash ex source 1 and id slash ex source 2. But is this correct? Are these conditions correct? Or are they wrong? Can somebody tell me where they could go wrong? Where they could go wrong? Missing one part. What do you mean by missing one part? Doesn't check for RS2. It is checking for RS2. It is checking for RS2. Anybody? Okay, let me give you that example where things might go wrong. So this is actually, we'll call this condition, okay, this exact condition as B, okay. So this is where you require forwarding from mem to write back. So this is your normal case, but again, this is not still complete equation. Now let me give you an example. What if they write back into memory and next instruction fetches data from that memory location? Again, in that again is a different case. So that is what you're speaking about, load and store. Okay, so those conditions we haven't dealt with. So for load, we have analyzed, right? For load, can you solve the load dependency using only forwarding? Let's say I have load T0, 0 S0, and if I have add T1, T0, T2, can this hazard or this dependency be resolved using forwarding? Can this be resolved using forwarding? Again, just recollect. There was one problem related to this also, right? I showed an example. So here, this cannot be solved with forwarding alone. Okay, you need to stall. So that condition we haven't discussed. Okay, I'll come to that. So whatever dependencies or whatever hazards I'm discussing till now is excluding this load instruction. Load instruction is a special case that I'll discuss separately. Is that fine? So when you say write back into the memory, that is related to load instruction. I'll discuss that separately. Okay. Now coming to this case, okay, so I'll give you an example, a specific example, okay, where things might not go as you expect if you follow these conditions. Yeah, so that is where the problem comes. Okay, so can A and B both get satisfied simultaneously? This is one such example. Okay, so you carefully see the sequence of instructions. Okay, so the first instruction, destination, is acting as source here in the next instruction. And in the second instruction, also the source and the destination are same. And in the third case, third instruction, you are using that S0 as the source. Okay. So let us try to analyze in the pipeline structure what might happen. Okay. And then we'll come to know how exactly to modify if at all I have to modify some conditions. Okay. So again, at the end of clock cycle 1, we'll analyze with the same example. At the end of clock cycle 1, the data related to first instruction is available in if/id register. Now, at the end of second clock cycle, you have id/ex value to be stored. So S1 will be read as 1, S2 will be read as 2. Here, till this point, not an issue. And then it will calculate the value 3 and 4. So here, can you tell me what condition is getting satisfied at this point? So we talked about X hazard condition as A and mem hazard condition as B. Okay. So if you recall. So now what condition is getting satisfied? A or B? Is it a X hazard or is it a mem hazard till this point? So it's basically X hazard. So your destination here is matching with source here. Okay. Your destination here is matching with source here. And again, of course, it is not 0 and your edge write signal is 1. So you forward. Here, your condition is matching. So A is true. You forward 3 to the ALE. So till this point, not an issue. No issue at all. Okay. But if you go one clock cycle later, okay, so let's say I go one clock cycle later, meaning at the end of clock cycle 4. Okay. At the end of clock cycle 4, my first instruction is there in mem/write back. It is having the correct value, which is 3 for S0. And your S0 value was taken as 3 and it was calculated. And now you are supposed to write 4 into S0. And then your S0 is being used as source here. So at this point, if I just go by A and B condition, okay, if I just go by A and B condition, can you tell me what is getting satisfied here? Which condition is getting satisfied? Now tell me, is it a mem hazard or is it a X hazard? So if you check here, the destination in mem/write back, it is matching with the source in id/ex. So that condition is getting satisfied, meaning your B condition is getting satisfied, whatever we had called it as B. And at the same time, if you see, since this condition is getting satisfied, so does that mean I should forward the value of 3 at the input of ALU? Should I give 3 as the input? Okay, should I give, why should I not give 3 as the input? What is the reason? So by the time I execute this instruction, I should take the most recently updated value. Okay, because S0 is being updated by the second instruction also. I have to take the value which is updated by the second instruction and not the first instruction. Okay, so 3 is already an old value. Now the most recent value that is available here is 4. By just checking this condition, I should not forward from mem/write back to input of ALU. That will be wrong. If I forward this way, this is wrong. Okay. Now again here, if you check, condition A is also true. Okay. So then there are two possibilities. So should I forward from the output of from the ex/mem pipeline register, or should I forward from mem/write back register? So what should be given preference? As you know, as we have already discussed, what should be given preference? Should the S0 value be taken as 4 or should S0 value be taken as 3? Should S0 value be taken as 4 for the next calculation or should it be taken as 3? It should be taken as 4, meaning this forwarding is wrong. Okay. And you have to forward basically 4 to the input of ALU. Meaning what? Meaning what? So for X hazard, meaning whenever I want to, the condition, what I should do for checking if I have to forward from ex/mem is condition A only. There is no change in the condition A. Now, if I want to forward from the output of mem stage, that is mem/write back, if I want to forward to this stage, okay, so is it enough if I check for B condition? When should I forward from the output of mem to? This is already taken care. If A is true, you always forward from the output of X/mem, that is output of ALU to the input of ALU. You always forward from output of ALU to the input of ALU when you have a condition. But the problem now is to find the condition. When should I forward from the output of MEM to the input of ALU? When should I forward? I should be able to forward when B condition is there. Okay, when B condition is there, but A is not there. Okay, so hence the modification that you have to do is, this is X hazard detection. It will not change. It will be as it is. Okay, so this is basically what we called it as A. But for modifying the MEM hazard detection, MEM hazard is when we try to forward from output of MEM stage to the input of EX stage. Okay, so when exactly should I forward? Okay, so I should not just forward when this condition is true. Okay, so this is basically B, right? I should not just forward when B is true. Okay, what additional condition I should add? At the same time, A should be false. Okay, at the same time, A should be false. So I should add that also. Okay, and not of this. Okay, so when this condition is false, this is like you are checking for a B condition, and this is like you are checking for A not. So when B is true and A is not, okay, only then I should be forwarding from the output of MEM stage to the input of EX stage. You understood why now? Because there will be a problem when you have conditions like this. When add S0, S1, S2, and add S0, S0, some S3 or S2 sub register, and add, you are using S0 as source here. Okay, when you are when you have such instructions, okay, when you have such instructions, so you should not forward from this to this. Okay, you should be forwarding from this to this. So whenever A is true, you always forward from the output of EX to input of EX. Only when A is false and B is true, then you can forward from the output of MEM to the input of EX. So that is why the conditions get modified further. And this is exactly the A case. Okay, so if you see these equations, we have already derived as part of A. Okay, so that should not happen, whereas this condition should get satisfied. So that is basically the entire equation for MEM hazard detection. Okay, so this is basically your modified MEM hazard detection conditions. Okay, so now we have understood, right, how exactly we came up with the conditions. So at this point, I would like to clarify if you have any doubts in whatever I have explained. So any doubts till this point? Okay, because it's like a little bit important. You should understand, because unless you understand, you'll not be able to maybe do your assignment, which I'll be shortly giving it to. Why don't we have MEM to MEM forwarding? MEM to MEM forwarding, it's not that it is not there in the basic representation. We are not including it. Okay, in the basic representation, we are not including it. But of course, if you want to implement an advanced processor, you can have MEM to MEM forwarding also. So that is one assumption throughout our discussion. So we are only forwarding from X/X. Okay, so there might be a possibility where you might require MEM to MEM forwarding. That is a special case, which we'll not discuss here. Okay, but till this point, whatever I discussed, is it clear? Any doubts till this point? Okay, so now what we have to do is we have to include this and try to come up with the circuit. Okay, so it's not just enough if we talk about the equations. So we also have to talk about how the hardware might get modified, how the data path might get modified. Okay, so the MEM hazard detection, again, this is with respect to RS1. This condition is with respect to RS1. Again, a similar condition will be there with respect to RS2. For both the cases, you have to check. If it is B A bar, then only you have to follow. Okay, so these things you have to check. Now we have to modify this data path. Okay, so now what components will you require to modify the data path, that we'll see. So since our interest is, you have to come up with something called as forwarding unit, where you will be able to check these conditions. Whether it will require X to X forwarding or MEM to X forwarding. So those conditions you will be checking with the forwarding unit. If you want to do that, can you tell me what will be the inputs to this forwarding unit? what will be the inputs to this forwarding unit? I'm just concentrating on the data path which is getting modified. Since here nothing changes here and almost nothing changes here. So that is what I'm showing here. I'm just showing array/id. You have instruction fetch somewhere here, id/ex and x/mem and mem/writeback. So you know that rs1 and rs2 fields will be available here, and rd field you also pass rs1 and rs2 fields. That rs2 field to the id/ex register also. You know why we do this, okay? And then rd field also you set. Now tell me what will be the inputs to this forwarding unit. You know that rd field will pass on. Okay, the same rd field will be named differently according to which register is supplying it. Okay, so now you have x/mem register rd here, x/mem/writeback register rd available here. So can you tell me what will be the inputs to this forwarding unit? One is I have to pass rs1 and rs2. Okay, so I have to pass id/ex rs1, id/ex rs2. Okay, what else? You say again, I already talked about this. You should not just say register write. Where should the register write come from? Where should the register write come from? The register write should come from either ex/mem, or again, it should come from ex/mem and mem/writeback, because you want to check both the conditions. Okay, so initially id/ex rs1 and rs2, and then you send x/mem register rd. This will be useful to check for ex hazard. You also send the mem/writeback register rd to check for mem hazard. Okay, in addition to that, I'll be sending the register write signal which is coming from x/mem register. I should also send the reg write signal which is coming from mem/writeback register. Okay, so these are all signals which are inputs. Okay, so using all of this information, you will be calculating your forwarding unit will detect whether there is forwarding required or not. But then how exactly should I do forwarding? Okay, so for that, again, I'll move this unit. So here, all of the important information, you know what is happening. Just pass rs1 and rs2. I'll just push this id/ex for better representation. Okay, I'll just push this ex, id/ex register here. Of course, you know that your register file is here, and then you have if register also. Now, how exactly should I implement forwarding? So all of this is fine. I'm taking the inputs, the equations that I just showed you can be checked here. So based on the equations, you have to now start sending the signal, right? So where should I start sending the signal? It's basically here at the input of ALU. You have to either send the data that is read from the register file. Okay, so here is the data that is available from the register file. But in some cases, you have to send the data which is available at the output of x/mem register, or the data that is available at the output of mem/writeback register. Okay, so exactly you will be taking this value at the output of mem to reg. Okay, because that is where the value that is supposed to be written will be available. Okay, so in this case, what element should I include here? I should be including multiplexers, as somebody pointed out. So this can be passed as one of the inputs. So this can be the value that goes to the ALU. What I'm trying to say is you either read the value directly from the register file, or you have to forward, your ALU should take the value as input, which is available at the output of ex/mem. So that is for x hazard. Similarly, in some cases, I might have to take the value that is available at the output of mem/writeback. So there are three possible cases. So one is directly sending the value. One is taking the value that is available at the output of ex/mem register, that is for x hazard, or mem/writeback register, that is for output of ex/mem for x hazard, and output of mem/writeback for mem hazard. Okay, so you'll be needing a 3:1 multiplexer. Okay, so assume that you have a 3:1 multiplexer. Now, whenever you have a multiplexer, you need select lines. Now tell me who will be supplying the select lines for these? Who will be supplying the select lines for these? The forwarding unit. The forwarding unit basically takes all of these, analyzes the equations, And based on the equations, it will send two signals. One is whether you are supposed to forward RS1 field, okay, so or whether the forwarding is required for the RS2 field, whether the forwarding is with respect to first register or second register. Based on that, it will send two select lines. Again, these two select lines are of 2 bits each because it's a 3:1 multiplexer. Let's assume if it is 0, 0, the value will be directly taken from the register file. If it is 0, 1, then the value forwarded from the output of EX stage will be taken. And if it is 1, 0, the value that is forwarded from the output of mem stage will be taken. So it is 0, 0, 0, 1 or 1, 0. So based on that, based on the condition, you will your forwarding unit will take all of these signals as inputs, and it will generate two signals which are of 2 bits each. Okay, so each of these signals are 2 bits. Okay, so that is very important information that we should not forget. So you have to basically find the values of RS1 and RS2 for different cases. Now let's say if this condition, if there is no forwarding required, if you are reading the values directly from the register file, then you make sure that forward the RS1 forward RS2 signals are 0, 0. Then the value directly will be passed from the register file. But if this condition is true, what should be the signal status? If only this condition is true, then what should be the forward RS1 and what should be the forward RS1, RS2 signal? So here, this is with respect to what? This is with respect to RS2. And we are checking EX/mem and ID/EX. So can you tell me what is this an example for? X hazard and mem hazard? First thing, what is this condition for? To detecting X hazard. And here for this signal, again, I think I misplaced. So this is RS1. So if this condition alone is true, then you can say forward RS1 should be equal to 0, 1 and forward RS2 should be equal to 0, 0. If at all this condition alone is true, then you can say forward RS1 is equal to 0, 0. Then forward RS2 is equal to 0, 1. Is there any possibility where both of these will be true? Can you give me an example of instructions where both of these conditions are true, both 1A and 1B? I'm still talking about X hazard. There are two conditions, one which checks the condition with respect to RS1 and the other one which checks the condition with respect to RS2. Can you give me a sequence of instructions where both of these conditions is true? In that case, your forward RS1 should also be equal to 0, 1 and your forward RS2 should also equal to 0, 1. So that is again, as somebody pointed out, the instruction sequence could be add S0, S1, S2, and the second instruction is add some register. Destination here is not of that important, but source should be both S0. So you have to try and forward to both values. So here it basically means the same value can be forwarded to forwarded as both the sources if at all both the registers are safe. Both your RS1 and RS2, if at all it is safe, then I'll be able to forward both of them simultaneously. Okay, so that is one more important point to remember. Okay, and both sources are basically equal to destination of the previous instruction. Exactly. And again, similarly, I can check the same thing for mem hazard detection. If this entire condition is alone true, then you say forward RS1 is equal to 1, 0. And if at all this condition is alone true, then we can say forward RS2 is equal to 1, 0. And again, a special case is when you have add S0, S1, S2, add S3, S4, S5, and then you have add maybe S6 or something, S0 and S0. Okay. So in this case, this source is this destination is being used as source for both the sources. In that case, both your forward RS1 and forward RS2, okay, both will be equal to 1, 0. Okay, that can also happen. Okay, and there are some extreme cases, different cases also that might occur. So based on that, you should be able to tell me the condition for RS. Let me give you an example. Okay, so let me say that here you have S0, S3, but S S4 and S0. Okay, so here can you tell me what will be the case of forward RS1 and forward RS2? I think I made a mistake. Sorry. So let's say this is S3. Oh no, sorry. Okay, let me rewrite the equation. So first is like add S0, S1, S2 first instruction. Then we have add S3, S0, S4. Let's say then other instruction is add S4, S6, S0. So under this condition, okay, so when I'm executing this instruction, okay, so then your forwarding is happening to the RS1 field, okay, and while I'm executing this instruction, okay, so let me change this to. So I'm more interested in executing the third instruction. Okay, so can you tell me when I'm executing this instruction, what will be the values of RS1 and forward RS1 and forward RS2? So I'm executing this instruction. So forward RS1 should be 1, 1. 1, 1. You see here. So here for this instruction, third instruction, there is a dependency with respect to S0 also. Okay, S0 also, and there is a dependency with respect to S3 also. The S0 is dependency is X hazard or mem hazard. The S0 dependency. S0 dependency is mem hazard, whereas S3 dependency is X hazard. So both can be true at the same case, but for different resistors. Okay, so here the resistors are different. The resistors are not same. So in this case, can you tell me what will be the forward RS1 and forward RS2 signals? What will be forward RS while I'm executing this instruction? While this instruction is available in the EX stage, at the input of EX stage, let's say, what will be the forward RS1 and what will be the forward RS2 signals? Where is the first source coming from? The first source is coming from the X hazard, due to X hazard. So in that case, it should be 0, 1. And your second source is dependent on the first the mem hazard condition. So this should be equal to 1, 0. Okay. So these cases might also occur. So you have to be careful. There are many possible cases that might occur depending on how the instructions are there. Okay. So depending on that, you will might face different cases of RS1 and RS2 select lines. Okay. I think with that, I'll stop here. So if you have any doubts, I've discussed about the forwarding conditions in detail, and I've also discussed about the hardware modification. So next time we'll discuss about this special case. When you are having load and data dependency, okay, so load and data dependency, in that case, you might have to stall. So for this also, I have to come up with some condition. Okay, maybe you can take this as an exercise and try to see what will be the condition to detect this case. So this case you have to stall, compulsorily you have to stall, and then you still will be using forwarding. But first I have to detect when to stall, and we also discuss how to stall. Okay, so I initially talked about stalling, meaning is equivalent to NOP operation, but what exactly happens? So all of that we'll be discussing in a minute. Okay. Is there any doubt with respect to today's class? Anything you want to clarify? You can clarify if you have any doubts. If not, again, I just want to ask you about midsem. How did it go? How was your midsem exam? Easy, difficult? I think except for one question, everything was easy only, straightforward, right? And maybe again you had to think a little bit for branch prediction case. Everything else was straightforward. So the average might be on the higher sides. Can I expect, again, I've corrected only few papers, so I'm not sure. I think many people have not answered that load question I talked about, right? Modifying the data path data path to include only instructions related to load and store without displacement. Okay, so there is no displacement. So you directly take this as address and then load from that address into this register. So not many people have done, at least the papers that I have corrected. And the branch prediction also people have gone wrong. Okay, mainly with respect to the states. Okay, so the ALU will still be needed. ALU, why won't ALU be needed? Because there are still RTech instructions to handle, right? So here, what happens is you will have instruction fetch, then you will have a register file. Okay, then what happens is initially in the earlier data path, you had an ALU. If the ALU was being used for address calculation, hence the memory stage used to come after ALU. But here the memory stage can come in parallel. Okay, and then based on this, you can decide what to write. So your mem2reg register mux will come here. Okay, so this is how the data path would look like. So I think many of you have written, at least the papers that I have corrected, they have written that there will be no change in the clock period, but there will be change because now both of them can act parallelly, because your address calculation for load and store has entirely removed. Okay, so in that case, what you do, the whatever you get from the register content is like an address. You can pass directly that address to the memory. You don't have to pass it through the ALU. So that way, both of them can be put in parallel in a single stage. Okay, so hence your that was the advantage. Okay, your clock cycle period will reduce, and both of these can be there in the parallel stage. Of course, they cannot be running parallelly because it's a single cycle implementation. Only one instruction will be there in the entire data path at any point of time. But this is the main advantage that I was looking for. And your earlier clock cycle period would be 1400, and the later the clock cycle period will be 1200. So if you have mentioned this, again, many of you have got this correctly. Again, many of you have got this wrong also. That is another thing. Okay, again, I'll go through the solution, your solutions, and based on that, I'll answer. But this is what I was actually looking for. And there is one more very common mistake that people have done. The times be different. That is irrelevant, right? We have to take the worst case scenario. What is the clock period for the worst case scenario? That is what we have to look at. You still have to consider the reg rate, right? So just like we calculated the worst case as load instruction, and for that we had calculated the clock period, you do the same here. But only thing is, since both of them are acting parallel, whatever is the worst among these, they'll occur only once. Okay, so that way the ALU will not come in the calculation of the clock period, because load will not use ALU. Okay, so that is how you'll. And one more thing with respect to the control signals I observed. So PC source, again, there were different sets, whether you knew or no, I'm not sure. There were two different sets I had prepared, at least for some questions. But in both the sets, I had asked for, I think in some set I had asked for control signals for add, and another set I had asked for control signals for store. Many people have written the control signals as don't care for PC source and branch. Do you think is this correct? What is the meaning of don't care? Can you tell me what is the meaning of don't care? What is the meaning of don't care? What do you understand by don't care? Don't care meaning it is not either 1 or 0. It's not just either 1 or 0. It basically means that if it is 0 or 1, it will not affect. Do you think if it is 1, it will not create a problem for PC source and branch? So if I put it as X, will that be correct? X meaning I can take it as 1 or 0. It should still work correctly. Now, if I take it as 1, then it should still work correctly. But for add instruction, are you supposed to have PC source and branch as 1? No, it should not be. Okay, so don't care you have written, then it is wrong answer. Okay, it's wrong. If you have written don't care as for PC source and branch, then it is wrong. I think it is already available in the slides. It's not like I have asked you to calculate something new. The slides also we have discussed exactly the same thing for store, and for these two branch instruction. So definitely you will be able to know. So branch instruction is one only for branch instruction for all the cases it is used. Okay, so that is again wrong. And related to branch prediction, the information was you had a single entry. Okay, so if earlier branch instruction, which was BEQ, okay, if BEQ was not taken, then this would remain as 0, 0. But when BGE accesses the same, it will still predict not taken. But had this outcome be taken, okay, had the outcome for BGE is taken, what will happen to the state? What will happen to the state? Will it remain 0, 0? Will it remain 0, 0? No. Again, people have done mistake there. Here the state will change. So the state will change as 0, 1. It will still predict, of course, not taken. So that I think maybe I should have given a better example so that you would not have got marks for that if you had not given the correct state. But luckily for some of you, it is still predicting not taken. But the state you have gone wrong. So when I am coming to this again, this branch again, so the state should be 0, 1. It will still predict not taken, but the state will be 0, 1. So at this time, if it is not taken, again it will go back to 0, 0 state. So the same state is getting modified by both the branches. So that's what is the meaning of single entry being there. Okay, so that also I think again, luckily for many of you, the predictions were not taken in all the cases, most of the cases. So it did not create a problem, but state people have got it wrong. Okay, so this was again one of the trickier. Again, it should not trace tricky. You had some work to do there. Based on that, you were able to. I think you should be able to come up with the branch prediction. Do you have any doubts with respect to any other questions that were given in the midterm exam? I think hopefully everything was clear. The program again, the instructions that you had to add was simple enough. You just check the last bit, so you had to add and a instruction, and then you had to add maybe 3 add instructions: one to update T1, one to update T2, the other one to update the stack pointer. Okay, all add T1 comma T2, T1 comma T1 comma 4, add T2 comma T2 comma 4, and add ST comma ST comma 4. Those are the 3 instructions. But the important instruction was and I S2 comma S2 comma 1, or again S2 comma S1 comma 1. Both will be still correct. So and to check if the last bit is 0 or not for the even odd program that I had given. And many students started asking questions with respect to stack-based ISA. It has already been discussed in class. So stack-based ISA assumes that the operands are there in top of stack. Okay. So it will calculate some value if it is X and Y. So it will calculate the value and stores the result on top of stack only. So you had to assume that, and based on that, you have to write the program. Anyway, that's all from my side. If you have any doubts with respect to any of the questions, by sending the entire instruction code along the pipeline. You can, okay, so technically you can, but the pipeline register size will be unnecessarily high. Instead of sending just 4 bits, if you want to send 6 bits opcode, but 6-bit opcode plus function codes, if you want to send, you can still send, but that is like unnecessary, what do you say, unnecessary usage of resources. Okay, so if there are no more doubts, then that's all from my side. Thank you. We'll meet in the next class.